Okay, more discriminant problems. This time we're asked to find the value of q given that x squared plus q minus 3 in a bracket times x plus q is equal to 0 has non-real roots. So for non-real roots, we know that the discriminant is less than 0, and we might pick up a mark for communicating that to the marker. Okay, so let's identify A, B, and C. A is equal to 1, B is q minus 3, and C is equal to q. So q minus 3 all squared minus 4 times 1 times q will be less than 0. That's q squared minus 6q plus 9 minus 4q. It's going to be less than 0. So that'll be q squared minus 10q plus 9 is less than 0. This is another example of a quadratic inequality, so we'll need to make a sketch, because that's how we solve them. So it's a positive q squared, therefore it's concave down. We'll then find the roots of the function, so q squared minus 10q plus 9 is equal to 0. Two numbers that multiply give 9, add together to give minus 10 is minus 9 and minus 1. Minus 9 times minus 1 is plus 9, minus 9 minus 1 is minus 10. So q minus 9 is equal to 0, q minus 1 is equal to 0. And that will be q is equal to 9 or q is equal to 1. Concave down, I've got a root at 1 and a root at 9. So where the thing is less than 0 is underneath the x-axis, and that is a closed interval, and that is q is between 1 and 9. Okay, next question. We're going to show that the roots of k minus 2 in a bracket times x squared minus bracket 3k minus 2 close bracket x plus 2k is equal to 0 are always real. So we need to prove that the roots are always real. So the condition for the roots being real is that the discriminant is equal to 0. So the question is asking me to show that that's the case for all values of k. Okay, so there'll be a bit of an algebraic manipulation with this one. A is equal to k minus 2. B will be the coefficient in front of x, that's minus bracket 3k minus 2, close the bracket. And c is equal to 2k. Okay, so b squared, that's minus bracket 3k minus 2, close the bracket, all squared, minus 4 times a, which is k minus 2, times c, which is 2k. So square the negative, I've got positive, and that'll give me 9k squared minus 6k minus 6k plus 4. I'm going to put that across there, so minus 4 times 2k is minus 8k bracket k minus 2. So it's 9k squared minus 12k plus 4 minus 8k squared plus 16k. So just go through that again. So the minus squared will give me a positive, then 3k squared, all squared is 9k squared, 3k times minus 2 is minus 6k, repeat that, minus 6k again, minus 2 all squared is plus 4, I brought that across there, 4 times 2k, with the minus in front is minus 8k bracket k minus 2. Okay, so 9k squared minus 8k squared is k squared, minus 12k plus 16k is plus 4k, and I've got plus 4. Okay, we now need to prove that this expression is going to be greater than or equal to 0 for all values of k. Now, the way to think about that as an aside is thinking about what happens when I square values, and something that we can say is always true. if you square a negative result, you will get a positive result. If you square a positive result, you'll get a positive result, and if you square 0, you will get 0. So worst case, you get 0. If you don't get 0, you always get a positive result. So we can say that you always get a greater than or equal to 0 result. So if we can package this up as a squared bracket, a squared term, then that means it must be greater than or equal to 0, because anything squared must hold a value which is either 0 or positive, therefore greater than or equal to 0. So if we can package this up as something squared, then that will prove that that's the case. Well, two numbers that multiply give 4, and that together give 4 is 2 and 2. And that can then be written as a squared bracket k plus 2. So k plus 2 all squared is greater than or equal to 0 for all values of k. Therefore, roots are always real, and remember that the condition for roots being real is that this discriminant is greater than or equal to 0. Okay, let's try another one similar. So, given that k is a real number, show that the roots of the following equation is always real. So let's this time go for kx squared plus 3x plus 3 is equal to k. Okay, so that's kx squared plus 3x plus 3 minus k is equal to 0. A is equal to k, b is equal to 3, c is everything else, and that's 3 minus k. Okay, so that will be 3 squared minus 4 times k times 3 minus k. That's 9 minus 4k bracket 3 minus k. So that's 9 minus 12k plus 4k squared. So that can now be written as 4k squared minus 12k plus 9. So 4 9s are 36, and the object now is to get this written as a squared expression. Two numbers that multiply give 36, add together to give minus 12 is minus 6 and minus 6. And we'll drop the 4k in here. Both can be factorised further by taking out a common factor of 2, and that will be 2k minus 3 bracket 2k minus 3, which can be written as a squared bracket. Therefore, the discriminant can be packaged up as something squared that's greater than or equal to 0 for all values of k. Therefore, roots are always real. Okay, let's try one more. So, show that x bracket x minus 3 is equal to p squared minus 2 has real roots if p is real. So again, the condition being for real roots is that we can package the discriminant up to show that it's always greater than or equal to 0. So let's bring these across. That will be x squared minus 3x minus p squared plus 2 is equal to 0. So a is equal to 1, b is equal to minus 3, and c is everything else. That's minus p squared plus 2. So minus 3 all squared minus 4 times 1 times minus p squared plus 2. So that then will be 9 minus 4 bracket minus p squared plus 2. So that's 9 plus 4p squared minus 8, which is then 4p squared plus 1. Now, since p squared must hold a value which is always greater than or equal to 0, then 4p squared must always hold a value which is greater than or equal to 0, and 4p squared plus 1 must hold a value which is greater than or equal to 1. Therefore, roots are always real, and for that matter, unequal.